Hello everyone, this is Dr. Vivek Laha and today we are going to discuss linear programming problems and graphical methods to solve them. So we have seen different types of linear programming problems. For example, we have production problems, marketing problems, finance problems, transportation problems, assignment problems, agriculture problems, diet problems, and so on. It means that we can have these linear programming problems from different aspects of real life. Now, let us consider a simple linear programming problem with two variables only. Suppose we have a linear programming problem. We have this maximization of z, which is defined as x plus y. We have 2x plus 7y is greater than equal to 14, 6x plus 5y less than equal to 30, 7x plus 2y greater than equal to 14, and x and y are greater than equal to 0. So this one is the objective function, and these are the constants, different constants, and these are the non-negativity constant, non-negativity constants. So we have to find out the objective value which can maximize over these feasible regions. See, the points which satisfy all these constants are known as feasible region. So feasible region. So we have to find out all these constants, all the points which are in the feasible region, and then we have to decide which point will maximize the given objective function. So what are the steps to solve this linear programming problem graphically? So the first thing is to plot the feasible region. So we will plot this feasible region, and then what we will do, we will locate the corner points in the feasible region, and then we will find out the value of the objective function at the corner points, and then we will compare those values and decide which is the point where we have the maximum value of the objective function, which is the point where we have the minimum value of the objective function. So first, let us try to plot the feasible region of the given linear programming problem. So we have this graph paper, and now we can see the first constant was 2x plus 7y greater than equal to 14. So first we will plot the equality constant, that is we take this 2x plus 7y equal to 14, and the simplest way is to find out 2 points on the x-axis and y-axis and then to plot it. So suppose we have this value of x and we have this value of y. Suppose this x is equal to 0, then y will be 14 by 7, that is 2. And when y is equal to 0, so x will be 14 by 2, that is 7. So we have 2 points. This point is 0, 2, that is on the y-axis we have this 0, 2, and the other point is 7, 0, that is on the x-axis. So we have this 7, 0 on the x-axis. So what we have to do, we have to just join these 2 points. So we will have this blue line that represents 2x plus 7y equal to 14. Now this blue line divides the plane into two parts. One part contains this origin and the other part does not contain the origin. So now we have to decide which part of this plane is represented by this inequality. So suppose we have 2, in place of x and y we substitute 0, and this is greater than equal to 14. So you see this is 0 is greater than equal to 14, which is false. So it means that the portion of the feasible region or portion of the plane which is represented by this inequality does not contain the origin, and that is we denote it by this arrow. So this upside, the upper part of this blue line will represent this inequality 2x plus 7y greater than equal to 14. So similarly, we can plot the feasible region 6x plus 5y less than equal to 30, and you can see this is represented by this line, and it intersects the x-axis in 5 0 and y-axis in 0 6. And now again we have to decide that which part of the feasible region this contains. So we can plot the 6 0 and 5 0 and less than equal to, this is 30. So you see that this is 0, which is the equivalent of 0 is less than equal to 30. So which is true. It means it represents the part of the plane which contains the origin. So it is the portion below this red line. Now we have to plot this third constant 7x plus 2y greater than equal to 14, and this is represented by, so you just try to plot. You see this line intersect x-axis at 2 0 and y-axis at 0 7. So you have all these lines, and again if you if you try to check which part of the uh, plane will be represented by this inequality. So you just substitute 7 in place of x 0, 2 in place of y 0, greater than equal to 14, and you see that this is equivalent of saying that 0 is greater than equal to 14, which is false. It means it this inequality 7x plus 2y greater than equal to 14 represents the part of the plane which does not contain the origin, and so it represents this portion. So now you can see, or you can observe that the portion of the plane which is contained by uh, all these inequalities, or satisfied by all these inequalities, is the region bounded by this triangle, that is this blue line and red line and green line. So now we have plotted the feasible region out of these constants. Now the next thing is to find out the critical points of the feasible region. So what are the critical points or corner points of the feasible region? So the corner points of the feasible region are the points which are points of intersection of these lines. So you see this is the intersection of blue and green line, this is the intersection of this red and blue line, and this is the intersection of green and red line. So we have to find out the corner points of the feasible region. So we have 3 corner points of the feasible region. So what we can do, you just try to solve the constant 1 and constant 2, and if you solve this c1 and c2, you will see that a is 35 by 8 and 3 by 4. You just have to solve the linear equations in 2 variables. So you just solve c1 and c2 so to get the value of a. Now if you solve for b, you will get b as 10 by 3 and 126 by 23, and for c you will have 14 by 9 and 14 by 9. So what you have to do, you just solve c1 and c2, then c2 and c3, and then you solve c1 and c3. So on solving the that is whatever equations you have, you just take 2 equations out of the given equations and solve them for the values of x and y. So once you have the corner points, so we have 3 corner points a, b and c. So once you have the corner points, you can find out the objective value. So what we have to do, we have to find out the value of the objective function at the corner point. So the objective function is given by z equal to x plus y. So at a, it is 35 by 8 and 3 by 4. So you just add up 35 by 8 plus 3 by 4. So you will have this 41 by 8, which is 5.125. Similarly at b, you will have the value 5.913, and at c you will have the value 3.111. So you can see the maximum value obtained by these by the objective function is 5.913. So this point B is the point of maxima, that is max maxima, and the minimum value obtained by these points is 3.111, which is obtained at C. So this point C is the point of minima. Okay, so now once we have this objective value, what we can do now, we can see that the question is that what are the points. Now the questions are that why are we considering only the corner points of the feasible region and not the other points? And the next thing is it possible that the other points of the feasible region are also optimal? So to answer these questions, we have this optimality at the corner points. So let R be the feasible region, which is a convex polygon, and for a linear programming problem, and let Z equal to AX plus BY be the objective function when Z has an optimal value, maximum or minimum, where the variables X and Y are subject to constants described by linear inequalities. This optimal value must occur at a corner point vertex of the feasible region. So you see this is very important, that if it is not a corner point of the feasible region, then you will not have the optimal value. The next thing is that the theory of the bounded and unbounded feasible region. So if let R be the feasible region for a linear programming problem, and let Z equal to AX plus BY with the objective function, if R is bounded, suppose this R is bounded, then the objective function Z has both a maximum and a minimum value on R, and each of these occurs at the corner point vertex of R. As we have seen already in the previous example, that we obtained both maxima and minima because the feasible region was bounded by a triangle. Now, if R is unbounded, suppose it is unbounded, then a maximum or minimum value of the objective function may not exist. However, if it exists, it must occur at a corner point of R. So all these results you see, they establish the importance of this corner point. Again, if you have this multiple optimal solutions, so if two corner points of the feasible region are both optimal solutions of the same type, that is both produce the same maximum or minimum, then any point on the line segment joining these 2 points is also an optimal solution of the same type. So we will discuss these results in detail later on, but let us see and linear programming problem with unbounded feasible region. And you can plot this feasible region. You see these are the constants, and you just try to plot this feasible region, all the feasible regions. So you can see this part of the linear programming problems. So this is the upper part, all these, so above this line. So you have all these are the corner points. You just find out the values at these corner points, and you see that the objective function can move from one place to other, and if you keep on increasing the value of the objective function, you will see that the feasible region is unbounded. Suppose in this example, you can see this is the feasible region, and this is the feasible region, and the objective function is objective function. You can have multiple optimal solutions. So similarly, you can have a linear programming problem with infeasible solution, and see this is the objective function, and this is the this is the program. So you see that one value is above this and other is below this. So you can have you cannot have some common solution which satisfies both the inequalities, and hence this is an LPP which is infeasible. So there are different types of formulation of this linear programming problem. Later on we will discuss the theory and results in detail as well. So what are the conclusions that okay, thank you for joining.